The interlocking mechanical gear is a fundamental building block of human engineering. It is the core component of our factories, our vehicles, and our clockwork history. We usually credit this invention to the ancient Greeks, or the engineers of the Industrial Revolution. But while these groups refined the gear for human use, they weren't actually the first to develop it. Millions of years before humans walked upright, evolution had already developed and deployed this exact mechanical system. This incredible, futuristic technology is currently operating right now, hidden away inside a common insect that lives in your own backyard. Our mechanical history is significantly younger than the biology it mirrors, setting the stage for a complete teardown of what we consider human invention. This is Isis coleopterus, the common planthopper. It's smaller than a grain of rice and, at a glance, looks like a boring piece of walking tree bark, but its performance is extreme. This bug launches itself forward at 8.7 miles per hour in under 2 milliseconds, an acceleration of 400 Gs. For perspective, that force would instantly liquefy human organs. To jump straight and survive that launch, the bug requires perfect synchronization. Both hind legs must push off at the exact same fraction of a microsecond. If one leg fires even a 10,000th of a second late, the offset thrust sends the bug into an uncontrollable midair spin. Biological brains are simply too slow to coordinate this. Neural signals take time to travel down a body, and microscopic differences in nerve length would cause a fatal delay. The bug cannot rely on its nervous system. It needs a physical hardware bypass. In 2013, researchers at the University of Cambridge placed these jumping nymphs under a scanning electron microscope to solve the synchronization mystery. They found an anatomical anomaly, literal interlocking mechanical gears at the planthopper's hip joints. When it crouches, the teeth physically mesh together. When it jumps, the mechanism forces both legs to rotate at the exact geometric instant, ensuring perfect physical synchronization. Evolution bypassed organic coordination entirely. In this specific moment, the organism survives by functioning as a literal machine. The design is highly specific. Each tooth features asymmetrical filated curves at its base, rather than sharp 90-degree angles. These curves serve a vital purpose. They distribute stress and prevent the gear teeth from shearing off under high torque. This is the exact engineering solution humans use in modern car transmissions to keep metal teeth from snapping under pressure. But there is a biological catch. When the planthopper reaches adulthood and sheds its exoskeleton, it loses the gears, switching to a friction-based jumping mechanism. Rigid mechanics carry a heavy risk. If one tooth breaks, the entire machine is dead. Nymphs can regrow a broken gear during their next molt, but adults can no longer shed their skin. They cannot afford to rely on a mechanism they can no longer repair. Nature integrated mechanical engineering with long-term risk management millions of years before the first human factory was built. This insect challenges the boundary we've drawn between messy biology and crisp engineering. We often assume that interlocking geometry is the exclusive domain of human logic. This discovery is actively influencing the development of nanotechnology and microscopic robotics. Instead of relying on human blueprints, engineers are studying these insects. Evolution has already spent eons performing the trial and error required to make microscopic machinery work. We often look toward the stars for advanced technology, but there are complex, interlocking machines operating in the dirt under our shoes. We are just beginning to identify the mechanical secrets hidden in the natural world. If you want to keep exploring these hidden systems with us, hit that subscribe button. Stay curious, and I'll see you in the next one.